So this is the page which shows the functions for normal distribution available in the scipy library. So there's the definition of its density function, then cumulative function, then there is the inverse function. And okay, let's explore that one. Normal distribution, what functions are available? So from scipy stats dot norm. So that is to access the functions from the normal distribution. So there are some examples. Of course, we will do these examples with our with our Jupyter notebook. So there is first function, random variates. So it says location 0. It means it is defined for standard normal distribution. Mu is equal to 0. Then scale is equal to 1. Scale is the standard deviation, right? And size means the number of values you are interested in. So these are going to be the random values taken for a normal distribution, which is governed with mean value 0 and scale equal to 1. If you want to look for the probability density function, so for a standard one, you can provide x, then location is the mean value, scale is the standard deviation. If you do not provide, automatically they are going to be taken as the standard values. Then CDF, cumulative distribution function, is there. And also there is one percent point function, right? Percent point function requires the probability value to be specified, and then it is going to give you the x value with that. So let's define these things. So the first thing, we have to import the libraries, numerical Python library for defining vectors, then scipy stats library to access these functions, and then the plotting library. So let me first run this set. So now the values which are available from the tables, we can access those values from here as well. So for example, let me first define some x value. So I would say numpy linear space, say -3 to 3 with some 100 values. So that would define x for me. So that is the x values have been generated, right? Now let's define f of x function. I'm going to define the density function, right? So density function, I can define SPS norm. We have x values for all x values, right? Define the so location is 0 and scale is 1, right? Location 0, scale 1. So this will be generated, and then I can plot it with the matplotlib plt plot x and f of x, say with some red color, and I would say plt show. Yes, SPS. Oh, I have not defined whether I require PDF or CDF. So I require PDF function, right? So this is good that we have got an error. It is good for demonstration purpose. So standard normal distribution. It means it has computed, it has provided us these ordinate values of the density function, right? Similarly, if I look for the PDF, so CDF, then let me call it with fx. In Python, small fx and capital Fx, they are different, right? So I call SPS for normal distribution and CDF and x, right? The other parameters are understood. Okay, I didn't plotted that. So let's plot PLT plot X and FX. I would say with plot with blue and PLT show. So the monotonically increasing function, right? So it means all the data, all the integral values which are tabulated in the books, right? They are now accessible to you. So for example, what is the probability from minus infinity to 0, right? So for that one, I would say SPS CDF, right? SPS norm dot CDF, I would say up to 0. So that answer should be 0.5, right? The integral from minus infinity to 0, this is the half part of normal distribution. And the other test, let me do it, that we always say that there is about 68% of the data within one standard deviation. So in order to access that from standard distribution, I would say norm CDF -1, right? And here let's write SPS norm dot CDF1 minus this, right? So cumulative area up to 1 and cumulative area up to -1. It has been subtracted from it. So the answer is 0.689, right? Now the percent point function. For percent point function, I would like to check the value. For example, I got the value SPS norm CDF 0 equal to 0.5 here, right? So the inverse of it, SPS norm percent point function of 0.5, right? So that would return me the value 0, right? So it is inverse of it. So from probability to FCSA value, right? So I have provided the probability, and now what's the FCSA value? That is 0, right? If you change it to say 1, so you will get some maximum value because normal distribution saturates at infinity, right? So theoretically, this is true. Then the last function, which is very important for us, that is for random variables, right? Random variates. So I would call, that is the computer generated data that conforms to a normal distribution. These are the values of X. It means it is equivalent data to a normal distribution. Very nice thing. So I will work with my experiment, SPS, norm, and random variates. For this case, I have to provide the location first, then the scale parameter, and then I have to provide size, right? So, let me just start with the first demonstration. Okay, I do not provide anything, right? It will take the default parameters and will generate one random value, right? So this one random value belongs to a normal distribution. But in order to simulate some 100 values that conform to a normal distribution with mean value 0 and standard deviation equal to 1, we have to write this function in a slightly different way. I will do it here. SPS norm RVS. So now let's generate a vector for it. So I would say location 0, scale 1, right? And I would write size equal to 5. It will generate 5 values. Of course, they are based upon some intelligent algorithm, Monte Carlo algorithm. So a vector has been generated, right? A vector of these values. What is the benefit of it? Let me take one example of it, that this is the data that conforms to a normal distribution, and it will have these all properties of the normal distribution, right? So for that case, let's define a size, say 1000, right? And then I define a vector S. So SPS norm dot RBS 0, 1, and n, right? So this has been generated. Now let's compute. Um, let's compute the mean value for it, right? So I would call numpy mean of S, right? And also let's call S standard deviation of S, right? So mean value is 0. These are 1000 values generated by computer, right? S is a vector that contains 1000 normally distributed values about mean 0 and standard deviation 1. And we have got this result, right? So these values are very important, very nice. Let's calculate the probability from this part, right? Let's count the values which are between -1 and 1. So you will be amazed that it is same as the probability between -1 and 1, right? I have generated that computer distribution, and now I'm counting. So I say I count equal to 1, right? I write for I range in range n, right? So if s of I if s of I is greater than -1, right? And s of I is less than or equal to 1, in that case I count equal to I count plus 1, right? And to end this one, I just have to end the tab, right? If s of I is this one, okay. Well, the counter should start from 0, right? And let's write the print probability. Probability will be equal to I count divided by n, right? So this is with the S vector. Probability is 0.674, 0.68. So if you use the more samples, let's test it for 10 raised to the power 5 particles. Let's run it. So see the mean value and standard deviation, right? And here it is. It has approached to this one. One last test in one line, right? If I develop a histogram for it, let's write here. Well, I have to write here. Okay, ABC equal to PLT hist X in 40 bins and PLT show. Let's develop its histogram plot. Oh, it has crashed. Okay, it seems we are running short of time. We will continue with our demonstration. Oh, not for X. Oh, sorry. S. These S values, 100,000 values were normally distributed, and they contain all the properties of normal distribution. So generating random variables, right, give you facility to get all the properties contained in a normal distribution.